word we English speakers use to describe the smallest measurable unit of mass is atom, a word derived from the 15th century French word of a different spelling, atome, which in turn was derived from the Greek word atomos, which means indivisible. But what would seem like the smallest unit of matter possible is actually made up of 3 types of subatomic particles: protons, neutrons, and electrons. The amount of protons contained in an atom is what you would find on the periodic table as the atomic number, the number that differentiates one atom from another. The number of neutrons contained in the nucleus, however, are what determine the isotope of that specific element. Some isotopes of an element are stable and therefore more common, as they are less likely to decay due to the number of protons being balanced with the neutrons. Other isotopes, however, are unstable and therefore radioactive, meaning that they have a half-life, or the time it takes for half of a given radioactive sample to decay. This decay of a radioactive isotope emits alpha and beta particles, which cause radiation sickness and other disorders in humans. While positively charged alpha particles lack the energy to even penetrate human skin, they can be very harmful if radioactive material is swallowed, damaging internal organs and ripping apart and corrupting human DNA. Negatively charged beta particles are almost the opposite in the way they affect people. They are smaller and faster and will pass right through clothing and skin, but are not quite as damaging as alpha particles when it comes to human tissue. Speaking of human tissue, cesium-137 is often used for radiation therapy when treating cancer, targeting a specific area of the body or tumor. This is one of the many known uses of radioisotopes in the medical field. Another more obscure use of a radioisotope is to detect art forgeries using radiocarbon dating. In the 1940s, 50s, and 60s, there were a multitude of above-ground nuclear weapons tested on American soil. These tests effectively doubled the amount of carbon-14 in the atmosphere at the time, affecting the amount of carbon-14 in anything manufactured after the first nuclear test. Given this information, scientists can detect if a piece of artwork was made after this period in time, based upon the carbon-14 content within a sample of the artwork they are testing. The last use of radioactive isotopes I will cover in this video is as a means of power, but on the small scale rather than an industrial scale like a nuclear power plant. If you're building a small spacecraft that has to support a lot of instruments and equipment reliably for years or even decades, you can't exactly just stick a battery on the spacecraft and expect it to last that long. The battery has to have some way of getting charged. One way NASA has done this over the years is via the use of a solar panel, which simply captures energy emitted from the sun. But another power source NASA has been using for the last 50 years is plutonium-238, which has a very high power density and also has a half-life of 88 years, meaning it can power spacecraft reliably for the better part of a human lifetime, which makes it an obvious choice for probes and other unmanned spacecraft. In conclusion, the uses of radioactive isotopes span almost infinitely further than the somewhat narrow scope of this video, and if you want to read more about the documented uses of radioactive isotopes, then you can click the link in the information card right here. Thanks for watching, and I'll see you next time.